Yeah, hello everybody. As promised, I want to help you for preparing for the exam next Friday. So I put together a spreadsheet called Markowitz, and it has calculations showing you how to do all these relevant calculations for the optimum complete portfolio, optimum risky portfolio, and also calculating the efficient frontier. And yeah, so I would say let's jump into it. You can see here the so-called input spreadsheet. The input sheet is obviously consisting of 3 time series. It's Microsoft, Tesla, and McDonald's. You can see it's daily data, 25th of September, 26, 27, 28, 29. And it's obviously it's 5 years, it's starting 5 years ago. And here in those columns, GHI are calculated daily returns. Simple daily return, as you know. And here in this section, I calculate the daily average return. Mittelwert or the mean value. So it's 0.11% on a daily basis for Microsoft. It's 0.28% for Tesla. It's 0.05% for McDonald's. Then I transform it into monthly data. So I calculate the daily data. I multiply the daily data by 21. So this gives me then the monthly data. As you know, it's not super precise, but as it's about expectations anyway, we don't want to be super precise. That's a waste of energy and a waste of time. We do a similar thing for the standard deviation, so we calculate daily standard deviations, STDEV function or STABW in German, STDEV in English, and so this is then 1.9% daily standard deviation for Microsoft, and we transform it into monthly data by, as I told you, multiplying it by the square root of 21. So this is important, don't forget it. Square root of 21 multiplied with the daily standard deviation gives you the monthly deviation, standard deviation. Then there is also, as you know, with Markowitz is of utmost importance correlation and covariance. There are several ways to do so. If you have only 2 time series input, if you have 2 variables, it's super easy because there's only one correlation and one covariance. But if you have 3, then you have already 6 numbers to calculate, and then it goes more and more. So I would suggest to use this function, this inbuilt function from Excel, which is applicable when you open data and data analysis. And data analysis has something like, in these analysis functions, of course, you have to first activate that add-in to have these analysis functions handy. But there is covariance and correlation. So if you click on covariance, for instance, you can input the return time series. Don't input the price series. This would be totally wrong. So you have to input the return series, as I did it here, GHI, and there is the the output section is starting in cell L4. L4 is obviously, it's here. That's the covariance for the daily data. Unfortunately, Excel is only calculating part of the correlation matrix, so you have to fill in the empty cells. And as I did, you will find it out. It's very easy to see once you have the spreadsheet handy. And then of course we have to also transform the covariance with daily data input into covariance for monthly data. And how do we transform this? Well, it's the covariance, so we have to use the number of observations per month, and numbers of observations per month is obviously 21. We have 21 trading day per month, so we simply multiply the daily covariance by 21. Let's check it out. Formula, as it's 21 times the daily covariance. So that's almost it. Now we have to remember what the Markowitz portfolio selection theory is all about. Well, we have two equations, as you remember. One equation is describing the expected return for the portfolio. It's this one here, 7.15. And the other equation is describing the risk, so the standard deviation of the portfolio. This is 7.16. 7.15 is super easy. It's simply multiplying two ranges in Excel, two vectors. Equation 7.16 is a little bit more difficult because, as you can see, you have two sum signs and you have the covariance. And there are several solutions to this. In the Bodeke and Marcus textbook and in the spreadsheet I showed you so far, I used the so-called bordered covariance matrix solution. But I think even more professional and probably a better way to solve this is using matrix algebra. So in this spreadsheet, I provide you both solutions. I show you now the first solution. This is what we've done so far. And then I show you the second solution, which I would suggest that you should be familiar with, because it's for you, it's then easier at the end. So let's take a look at the bordered covariance matrix solution. In this spreadsheet, I simply use now inputs from the input sheet. This is stored here in this section. So the return and the standard deviations on a monthly basis. Then we need the covariance matrix, again on a monthly basis. And this is exactly what we've done in the classroom, what I showed you. It's important to know that all these weights add up to 100. So this is why I put in this little formula here. This is simply transposing these weights, so they are linked, these weights. Yeah. And this is just applying this little nasty formula here. So I refer to the Bodeke and Marcus. If you are insecure, why does it look like this? I don't want to repeat this again. Just want to show you how to do this in Excel. So at the end, you calculate here the portfolio variance. So it's the sum of those sums. It's the sum of sum. It's exactly, so it's the sum of these sums. The sum of sum, exactly what it says here. So then we're almost at the end. Then we have to take the square root. We have the standard deviation of the portfolio variance. And then we calculate also the mean. Portfolio mean is simply the weighted average of the returns, return vector, weight vector. And then we have to put somewhere our target return. Because now we want to activate the solver. In the solver, we have to say either you have to minimize something or to maximize something. In this case, quite often, we say we want for a given stated return target, we want to know the minimum risk portfolio. So how can we do that? Well, we open the solver. Solver is here. We see goal B27, that's the portfolio variance. You could also say B28 standard deviation is all the same. In this case, we want to minimize it by changing cells B22 to B24. Those are the unknown weights. Okay, here are some numbers because I did it before, but this is what we want to solve for. We say all these weights should be larger than 0, should be positive. They should add up to 100%. This is what we talked about in this B25 cell. And there is the portfolio mean should be exactly what our target return says. It should be 2%. So then we simply say solve. Okay. There's a mistake. We have to do it again. So portfolio mean, we want to minimize portfolio variance and say solve. Now it's for sure working. Okay, there's a solution. And there it's 38, 10, and 51%. So let's do another one. So you see there's a change actually. So let's say we want to solve for 3%. Again, hitting a solver button. And this is super fast. We do it again. And now you will see different weights here. So, okay, we found a solution, and you can see if we go for 3% solver return, we need 50.8% Microsoft and 27% Tesla, and so on. Huh? And portfolio standard deviation is no big surprise, slightly higher than before with the 2%. So this is one way that's absolutely fine. I'm happy if you feel fine with this. Just be aware of the fact if it's 4 or 5 variables, then you have to extend this and you have to extend the formula. So you have to play with the spreadsheet, and maybe you use this as a little exercise before the exam starts, because then you might not have that much time. So the alternative is now to use matrix algebra. You will see when I click now on this sheet, it's exactly the same like this one here. It's just we don't have to do these rather tedious calculations. So let's show you what I mean in a second. See, this is gone, this space here. This is simple. Everything else is the same, but this is gone. So all the input is the same. This is also the same. And now it's just the calculation of the portfolio variance is a one-liner. Here you have quite an ugly construction of sum of sums and so on. Here it's a one-liner, and might not be that familiar for one or the other of you, but take a look into this malt function. I talked a little bit about it before. When you remember, we used it for calculating what did we do with it? Calculate discount functions in the bond session. And here, so we have to multiply, it's a matrix multiplication. We have to multiply C21, E21. These are those weights we want to solve for, multiplied with the covariance matrix, and then again multiplied with the weights vector. So it's exactly what it says here. It's exactly this little formula here. Yeah, this is in this cell. So this is probably the most difficult part in this solution procedure. So then standard deviation is simply the square root of the variance, and the portfolio mean is the matrix multiplication, where we multiply out the weights with the expected returns. So let's check out if this procedure is yielding the same weights for a target return of 3%. So we know already the solution. The solution should be 50.8, 27.3, 22%. So let's check it out if this matrix algebra is giving us the same solution. So data solver. And again, we want to minimize portfolio variance. We want to change the weights in B22 to B24. And the restrictions are the same. So we hit solve. And we will see the result in a second, or 2 seconds, or 3 seconds. Here we are. And it's exactly the same weight, 50.8. It's exactly the same. Would be a surprise if it's not the same. Yeah. So I hope you see, if we extend this solution procedure to 5, 6, 10 securities, it's much easier once you've set it up like this. So you might want to play with this, maybe with this spreadsheet, and just play around with it and make some experiments. But I would, if I had to choose, I think this one is better. So let's calculate now the optimum risky portfolio. Well, you know the optimum risky portfolio is the one alongside the efficient frontier, but it's not containing a risk-free asset. Yeah, it's consisting of everything, but not the risk-free asset. And you know, it's also under some assumptions, it's also the market portfolio. So let's try to calculate this. Well, how can we calculate that? Well, we have to use the solver. In the 2-asset case, there's a closed form solution, but in the n larger than 2 asset case, we need to optimize. So this I didn't show you last Friday, so this is maybe the only slightly new piece of information. So again, this is taken from before, so there's nothing new. Correlation matrix the same, covariance matrix the same, and the portfolio variance, all these calculations are exactly the same like I used here. The only difference is I introduce now the risk-free rate. Okay, I say on a per annum basis, I assume it's 2% because it's US dollar based. You can also say 3%. You would have to look it up anyway. Then I divide it by 12 because it's my horizon is a monthly basis. So I have monthly returns. Therefore, I divide this by 12. You could also say my risk-free rate is a 1 month T-bill rate. That doesn't make a big difference. And the additional piece of information is that I put in the Sharpe ratio. Yeah. So we want to maximize now the Sharpe ratio. Don't forget the Sharpe ratio is it's the ratio, it's the essence, it's the angle of this tangency line, of this capital allocation line, of this straight line. We want to have this, we want to maximize that. Now we want to have as much extra return per risk as possible. So Sharpe ratio is defined as, it's also in my slides, as you know, you simply calculate it as portfolio mean minus the risk-free rate. This is this one, this part here, divided by the standard deviation of the portfolio, B28 standard deviation of portfolio. So obviously, let's say we make a guess. Yeah, let's say we put in 5% for Microsoft, let's say 90% for Tesla and 5% for McDonald's, we would have a Sharpe ratio of 31. Yeah, let's say another guess could be we want 0%, Microsoft 0%, Tesla 100%, McDonald's. We have only a Sharpe ratio of 12%. So as you can see, when you play around with weights, it has an impact on Sharpe ratio. So it's very natural to say, let's use the solver again and let's try to find an answer. So solver in this case is now maximizing what? Well, the Sharpe ratio. We want to maximize Sharpe ratio. Yeah. So we maximize Sharpe ratio again, the same old unknowns, the weights, and again the restrictions are also the same, but this time we don't have an explicit return target because we want to maximize the Sharpe ratio. So let's hit solve. Takes again some time, and we found the solution, and it's 55% Microsoft, 45% Tesla, 0% McDonald's. And we have a maximum Sharpe ratio of 33.16. The portfolio mean is close to 4%, standard deviation is around 11%. So that's the risky portfolio, the optimum risky portfolio, given the risk-free rate. And as I said, all the market participants in an information efficient market share the same information, share the same methodology to analyze the market, so that's in equilibrium, also the market portfolio. So this is independent from my risk attitude. What is not independent from my risk attitude, so if I'm less or more risk averse, is my complete portfolio. So the complete portfolio, if you remember, is a combination of risky portfolio and risk-free portfolio. And in order to use this closed form solution from the textbook, we have to make an assumption about my risk aversion. Okay, I showed you last week there are ways to do so with questionnaires and so on. And you could debate if it's accurate or not accurate, but it's you can't get around. We need this this piece of information. So let's say for the example, let's say my risk aversion is 5. Then I take results from before, the expected return of the optimal risky portfolio. This is just what we calculated. And the risk of the optimum risky portfolio is also what we just calculated. By assumption, my risk-free rate is 0.17%, and I simply calculate then using this one little formula from the Bodeke and Marcus textbook, the optimum weight of the risky portfolio is simply then the expected return difference from risky portfolio minus risk-free asset divided by the risk aversion divided by the variance of the risky portfolio. This gives me 58.5%. So the weight for my personal optimum complete portfolio is 58% market portfolio and 41 point something percent riskless asset. And the expected return of this complete portfolio is 2.3 because I simply multiply out the weights and the expected returns. And then I can also calculate the risk of the complete portfolio, which is 6.6%. And if I ask myself, okay, what does this mean? Risky portfolio in terms of Microsoft, Tesla, and McDonald's, I will simply multiply out this weight 58% with the weight of Microsoft in the optimum risky portfolio. So you could say, yeah, I want 32% Microsoft, 26% Tesla, no McDonald's, and 41% risk-free rate. So in order to round it up, what we can say with regard to Markowitz, I also put into the spreadsheet this simulation. So now we don't get confused. I hope I don't confuse you now. But in the 2 asset case, there is a closed form solution. In the n asset case, you have to optimize. But of course, you can always play around and you can simulate. That's a third approach. Sometimes simulation is stupid, sometimes it makes sense. So let me just again take a quick look at the simulation. So again, same inputs as before, also the covariance matrix as before. Now the only difference here is that we use random numbers which are generating my weights for the assets. It's like making a guess. And this is because we have 3 assets and the random number generator in Excel is giving me a number between 0 and 1. So I have to make sure that they add up to 100%. So this is why I introduced this extra line of code here. And then I also showed last Saturday, those students who were around, there's a very neat way in Excel to loop this function. This loop is hidden under this button. It's called fill, yeah, ausfüllen, fill in the English Excel. I don't want to go through this because you don't need it for the exam, but of course I invite you to think about it, and it's really nice and handy and it's very interesting. So I can only present you the results, and the results are quite interesting. Here you see the first simulation, then I go down. We have actually 2,000 simulations, so 2,000 portfolios with randomly picked weights. And all these dots, as you can see, these blue dots are one portfolio which are picked by randomness. And you can see all these dots. For instance, this one, this poor fellow here, this is obviously a very inefficient portfolio, because for the same risk, you can get much higher return. So if you're rational, if you're a prudent person, nobody would hold this portfolio because it's inefficient. So you can see, although we start selecting randomly the weights of the portfolio, there is it looks exactly like a border. No, it's a border line. It's this efficient frontier line which is emerging from this randomness. And you can see, well, what we just calculated. No? There is this blue line. This is the risk-free rate, 0.17%, and this is the red dot. Is the point where this capital allocation line is the tangency line kissing this efficient frontier line. And obviously, so this is the maximum Sharpe ratio portfolio, which is around, well, close to 4% return-wise and around 11.5% maybe risk-wise. This is exactly what we calculated here, no? 11% standard deviation and close to 4% portfolio mean. So that makes obviously a lot of sense. And this green spot here is the optimum complete portfolio. So this, you could say, well, I don't know why it is like where it is, because I didn't draw the indifference utility curves. I don't want to go through this again. This is not now part, I think, of what I want to show you here. But you should know that this is actually the point where the indifference curves have a tangents line, which is the blue line, and this is where those two lines are meeting. And again, this would be then, yeah, as we calculated in this line, in this sheet here, we have 2.3%, close to 2.4% return, 6.6% risk, so it would be this point here. And you can see, obviously, if you add a riskless asset to a risky asset, it makes risk-wise a lot of sense, because you have, again, this portfolio is much more risk efficient than these portfolios are. So this is what I wanted to show you. I will upload the sheet and the video soon. So please walk through the spreadsheet and try to play around with 4 and 5 assets, and be aware of the fact that don't take the covariances for granted. Yeah, they are not stable over time. Yeah, it's like the correlations, covariances can move, and so what this Markowitz optimization is showing you, these are the optimum weights within a historical period of time. No, were the best weights for the last 5 years. This doesn't necessarily mean this is the best weight for the next 5 years. So don't get too exaggerated about this procedure. On the other hand, of course, it's a starting point to ask questions like, okay, what are reasonable return expectations for the future? But this is not part of this spreadsheet. In this spreadsheet, I wanted to show you how to apply, I think, in an easy way, solver, the Excel solver package, in order to come up with information efficient portfolios. And I'm sure if you walk through the spreadsheet, you are able to make all the right calculations. Okay, so have fun and good night. Bye-bye.